Backend database applications rely on a good storage system for durability, latency, performance, and much more. SSD have been a great invention in the effectively the storage medium space compared to the old mechanical, drive with moving parts. SSD improved the performance 10 and if not even 100 times folds. However, SSDs as it stands today still have a lot of limitations, and just because with any other technology, anything that comes as new comes with its own sets of problems that are unique to it. Unfortunately, some of these problems have been solved, some of them are still lingering, and we are using SSDs, but it's not optimized to its full potential that we're intended it to be. In fact, we created even, if you can argue, more problems that didn't even exist in old hard drives. So in this episode of the Backend Engineering Show, I'd like to explain the basic building blocks of an SSD, how it actually works, and then illustrate these problems. And finally, I'll talk about some of the solutions that are being proposed to solve this. How about we jump into it and discuss? Welcome to the Backend Engineering Show with your host, Hussein Nasser. And the first concept that we need to discuss when it comes to SSDs is the idea of a block. You see, SSDs are considered a block device, which means that to write or to read from this medium, you can only read in a block worth of size. You cannot read a single byte. And the block varies. I guess this current sizes are 4K bytes, 4 kilobytes. So if you write a single byte, you're writing 4K. And if you're reading a single byte, you're reading 4K effectively. If you're reading 4K plus 1, whatever the actual bit conversion there, you're reading actually 2 blocks, not 1. So that's the basic concept here. So if I take an example here, and I'm writing a SQL to insert a single row in the orders table, for example, right? And the orders table have a lot of fields, maintain a lot of fields. And since I need these fields to be searchable, I create some indexes on these fields, right? So if I insert a single order in that table, I'm actually updating not only that table, but all the indexes or indices, if you're from the UK, to have the final, state of the table. So let's say I have this table, and you have 20 indexes on 20 different fields. Maybe you have composite indexes. You have to update the actual table data by inserting that row, and then you have to go to all the indexes and update those indexes with the new entry that you just made. This translates to a bunch of writes, right? So it can be the data file can live in its own file that belongs to the file system, and the indexes can live in its own, each index can live in its own file. And as a result, you are flooded with a bunch of writes, and these writes to the file system translate to blocks. So you're now writing a bunch of blocks, all sending it to the medium, to the SSD. Now we have a problem, right? Because how do I know if I'm going to update a certain block in the SSD? How do I know the address of that block? You might say, yeah, the SSD comes with a specific sets of addresses and you can reference those in the application. That's a bad idea, because guess what? If I want to update a block 1 in the SSD or block 10, I cannot guarantee that block 10 will remain, the content of block 10 will remain in block 10 in the SSD. SSD moves stuff around all the time. There is a process that we're going to talk about called garbage collection, where leveling, over provisioning, all that stuff. It moves that data. So if you kept a reference of this physical block address in your application, you're screwed. So that's why we need to talk about the second concept, which is the logical block addressing. So now the SSD exposed a concept called LBAs, or the logical block address. You can store this in your application, your file system, and you can make a reference of these blocks that you want to update or write to, right? And in the back end, in the SSD itself, I am going to create a mapping between the logical block to the physical block in the SSD. Basic stuff. Now, that means if I actually changed the location of a block, I just need to update this mapping. So logical block 1 points to logical block 10, and I change 10 to 20. It doesn't matter. I just change the mapping from 10 to 20. The application still sees logical block, the original one. It doesn't really change. So that's what the SSDs do today. Now here's a problem. Mapping. What does that mean? In order to build a mapping, you need to store it somewhere, right? Where do you store this, right? So the SSD, so this is effectively the translation of the mapping between the logical block to the physical block. And this is called the flash translation layer. The flash translation layer is a very critical piece in any SSD controller. It translates between the logical blocks that expose to the host to the physical blocks that are actually in the SSD. The problem with the flash translation layer is well, you're a programmer, you wrote some code before, right? In order to build a mapping, you really need to store it somewhere. Well, the SSD is responsible for this. It's not a problem of the host, right? So the SSD needs to come up with a storage mechanism to store this mapping. And you need it to be fast because you're going to read this all the time, this mapping, right? So now the SSD comes up with a concept called a dynamic RAM. So now it is shipped with something that you really didn't ask for. So SSD comes with a RAM that you can never use. You're paying more money to ship this RAM that you're never gonna touch, but it is also required. Why? Because the SSD is doing this thing that you never asked it to. This is called the flash translation layer, but it has to, right? So all the cost gets added up. Why? Because the reason is just block translation that is happening. So maybe someone one day will come and challenge that and says, hey, I'm okay. Don't touch my blocks. Please leave them as be, right? Maybe this is not feasible, but leave them physically there and don't ship me any RAM. I don't store any RAM, right? Obviously, the idea of flash translation layer can take less and less memory the more coarser the blocks are. What does that mean? It means if you do the addressing at a smaller block size, then naturally, if you have a large SSD, you're going to need a lot of entries, right? Because small means a lot, right? You're going to need a lot of blocks. But if you have coarser block, larger blocks, you're going to need less and less mapping, right? At some point, people wanted to do the addressing at the page level. A page is smaller than a block. A block has a collection of pages, but nobody talks about pages in the storage community for some reason. I think they try to avoid that, right? But if you do the page addressing, then you're going to need a lot of entry, which translates to a lot of RAM, which translates to more money. All right, so that's basically the DRAM, right? So understand that it exists and the reason exists and that the cost associated with it. The next thing we're going to talk about is the erase unit. For the longest time, to write to an SSD, you need a block or a set of block that has been cleaned and erased and ready to be written. If you have a block that is already pre-written, right, you cannot just override it. That's the rule, right? And it makes sense when you understand bits, It's like you cannot just take your bits and just slam it, right? You need to erase it and then write stuff to it. So you can do this. So, okay, let's, if I want to write, let's do this. I'm going to go to a block that's already bad or invalid. My write will do an erase and then a write to the same block. You can do that. But now writes are slow because you're doing two operations instead of one, right? So the SSDs almost never do this. What they do instead is they take your write, the set of blocks that you want to write, and slam them to a place that are already good. And then what they do is they mark these old blocks as invalid. And then obviously they do any logical mapping from the logical to the physical addressing and update the flash translation layer. So that's what they do today, right? That's what's happening. The problem is you're going to reach a stage where you need to erase. And here's how eraser is done. Because erasing is expensive in the SSD is doing it in larger units. You know, it's more than one block. And this is usually called the erase unit. Previously, they used to refer to the page you write in pages and you erase in blocks. But I don't see storage, the community storage, talk about these in these units anymore. I noticed that they are always referring to writing in a block and then erase in an erase unit. They don't want to refer to they don't want to give names anymore, and there's a good reason behind it, because it gets confusing. What is a page? What is a block? What is a sector? Right? So I like the usage of an erase unit, right? So that's the idea here. You erase in a big unit, but you write in a single block or more if you want. And then the concept of namespace. You know, in cloud providers, when you sign up as a customer in a cloud provider, and I also sign up as a same cloud provider, and someone else signed up, our content might be put on the same SSD, but you might say, what? That's dangerous. Not really, because SSDs come with this concept that's called namespace, where a namespace is a collection of the SSD that is of the SSD blocks that is assigned to a client. And this client is the operating system in this case, right? And the operating system will only see this namespace. It will not see the rest of the drive at all. So you cannot even claim that you're assigned this namespace or a collection of namespaces. I don't know if you can do that, but that's the namespace you're assigned to. So this is effectively the idea of multi-tenancy. So multiple customers can live in the same resource, the SSDs, and they can do completely different things, but they are isolated within their namespace. So that's another important concept, right, for multi-tenancy. All right, now that we explained the building block of SSD, let's summarize. You write in terms of blocks. You always use logical blocks. The logical blocks are mapped to physical blocks in the SSD. Why? Because the physical blocks always change, right? And the mapping is stored in the flash translation layer, which requires RAM, right? You want this to retrieve the mapping as much as possible. You can write in a block or multiple blocks, but you can only erase in an erase unit, which has a certain number of blocks. You cannot erase a single block, right? You can, but the SSD won't let you, right? For power reasons. Because the erase takes you apply a little bit more power to the cells behind the block, the erase and program cycle, eventually consumes the cell, and that cell eventually will die out. There is a certain finite number of program, which is writing and then erase, right? So do them in a larger set so they die together effectively, and instead of writing them and erasing multiple small units of blocks, right? So that's basically the concept. Finally, the namespace, where it's a collection of blocks assigned to a client so that it only sees this sets of blocks. And that's called the namespace. Now that we understand that, let's talk about the first problem, you can call it. You can call it things that it has to happen, but it causes a side effect. Garbage collection. What is that? When you write to an SSD, when you have file A and you file B and you write to the SSD, the blocks that comes from file A and the blocks from file B are interleaved together, right? There is no order, right? You cannot guarantee that all the A's will write first and then the B's, right? The block. They will come together. So the result, a block from A will sit next to a block from B, will sit next to from B, A, and then they will be next to each other. So the data is mixed up. There's no guarantee of the actual order in the SSD. We talked about that, right? And so what does that mean? It means if as you update the files, the old blocks will be invalid, the new blocks will be remapped, and then all of a sudden you want to insert a new file, right? So that file takes a certain amount of blocks and fills the gaps, if you will. And then finally you want to delete a file, and then all of a sudden that delete of a file invalidate all these blocks. But guess what? At a certain point, your SSD is full. So what does that mean? So a new file comes in, file X, for example, and you want to write it to disk. There's no space. Why? There is space available. It's just invalid data that needs to be collected and removed, right? So I can write. These are all data that nobody needs anymore, right? So I just need to write to it. But you can't. You have to erase to write. We talked about this, right? But guess what? We cannot erase a single block. We have to erase a single unit, an erase unit. And guess what? We do not have a clean erase unit. It has valid data in it. Wow. That sucks. What do I do now? I'm about, consider yourself an application, a database that you're inserting the SQL again. And you have this flood of blocks coming in, and your client all the way in the web application is waiting. But now the SSD says, wait a minute, I'm out of space. I don't have anything. So now what the SSD says, hold on, let me erase a unit. I don't have any unit to erase because there is data in every one. So one unit will have 3 blocks empty, and then a lot of one that is invalid. And then the second one might have few empty, and then the rest are valid data. So the SSD needs to erase a unit. All right. Sounds like a problem that can be solved. Let's pick an erase unit, right? There's a valid data. What are we going to do? We're going to move the valid data somewhere else temporarily, right? And then we're going to erase that unit, and then we're going to place the data from the user in the erase unit. Sounds like a plan. The question is, where do you move it? The SSD is full. Meet another thing nobody asked for. Over provisioning. So now there is an SSD area that you paid for that you cannot use. It's there and you cannot use. It's dedicated for the system. So there are 2 pieces now. The DRAM, you are not using that. The over provisioning, you're not using them. And both are expensive as shit. So you're paying for stuff that you're not using. Sucks, huh? So now the over provisioning is the data was moved to the over provisioning. So that's one write, right? So your original write, remember that. Original write comes in. No space. Well, let's pick an erase unit. Move the invalid data to an over provisioning area. Write to that. So that's one write. The second write, erase the unit. Erased. Nice. The third write, move the valid data that you moved back to the erase unit. That's the third write. And then the fourth one is actually your data. Boom. Right. And so your single write resulted in 4 writes. So now all of a sudden, your bandwidth that the SSD manufacturer claimed to have, you don't have that anymore. You said, okay, I can write 40 gigabits a second. No, you can't. Because in this case, one write translates to 4. So that means what is exposed to you is actually a 10 gigabyte per second. So now your bandwidth is killed because of this amplification. That's the second problem. Write amplification. What we discussed right now is called the write amplification. You do one thing, but the actual work that is happening is more. It's 4 times the writes that you actually did. Yike. See. And plus, this is over provisioning that you cannot use. Right? And here's something. There's another problem here. You see, when we move that valid data that belongs to whatever file, that existing file, we moved it to over provisioning. If someone issued a read to that poor slob file, that they want to read that file while we're moving it to the over provisioning so we can erase the unit, if someone made a read, they will be blocked. They will be waiting for that moving to happen, for that garbage collection to finish. So not only writes are slowed down, reads are slowed down as well, read our blog, and you're gonna see this all the time in form of fluctuation in your applications. Like, what does that mean? I wrote this, all of a sudden it's fast. The second time, exact operation, it's slow. What's going on? Right? Cosmic rays. That's, by the way, most engineers' solution to all this problem is like, oh, it's a cosmic ray. Something came from the sky and screwed a bit. I love that. One more note about over provisioning is that some smart South Korean researcher have found a way to inject malware into the SSD so that it never get detected. Why? How? They used the over provisioning. They stored the ransomware or the malware, the virus that can be detected easily, into the last LBA in the SSD. And then they used the admin API and the SSD to increase the over provisioning, effectively just shifting the over provisioning so that their file becomes in the over provisioning area. What happens when you do that? The operating system can't read it because over provisioning is considered a system area. And the OS cannot read it. If the OS cannot read it, any application on top of the OS can read it. That includes antiviruses. What a genius way to hide viruses, you know? So you can hide it, and when the time comes in, it can almost like hibernate, you know? And then when the times come back, you can activate that virus by shrinking the over provisioning and then running that virus. What a genius way. I'm going to reference the article and the video I made about that. So we talked about all this stuff now, garbage collection and over provisioning. We talked about write amplification. Now the final thing we're going to discuss is something called the where leveling. And no, this is not the question of where are you as a location wise. Nobody's asking about location. No, this is not the act of wearing a piece of clothing. And no, this is not the past tense of is. Where is a word that I recently learned, and it means to exhaust or tire. You say you want to wear your kids out during the day so they sleep better at night, right? So that's wearing. Wear, obviously, if you speak English, you understand. English is not my first language, so that's a new word for me. So where leveling is the idea of wearing all those blocks so they exhaust at the same time. You see, we talked about this program erase cycle, right? You can only program and erase certain number of times, right? Before this cells behind this block dies out. So you don't want to have blocks that are very active, writing all the time, and then blocks that are cold and nobody touch those data anymore. Why? Because this cells will die out while this cells will remain. And as a result, you will lose storage, and your data will be corrupted as a result, right? And this performance, this will translate to a lot of degradation of the SSD. So where leveling is the algorithm that says, okay, nobody touched this data for a long time. Let's just move it on. Let's just take this data and move it around so we can use the cells behind it for harder data effectively. So that's the idea of where leveling. All these problems exist today. There are solutions to that. Maybe we're gonna talk about in another video. I don't want to make this video too long, but there is one proposal called the zoned namespaces, where you expose the knowledge of the actual SSD to the host, telling the host that, hey, this is an actual erase unit. So what you do is expose the idea of an erase unit to the host so that if it writes a file, it specifies, hey, I want to write to this erase unit, also called a zone. So when your file goes to that zone and someone else's file goes to another zone and that file is deleted, you're fine. You are isolated. And the idea of segregation and isolation is actually good in this case. So erasing a zone and writing to a zone, your data is cleanly separated. And this separation is good for write amplification. The problem with this that I have doubts with this is go and teach the operating system and all this general purpose stuff to have knowledge about the zones. I feel this is gonna be every time we expose knowledge about the underlying system to the client or the application, the backend application in this case, becomes really complex. We see this with sharding. Sharding is really complex because the client needs to understand, oh, this table is in this database, and this instance on this IP address. Oh, this table is in this instance, and this, and this becomes really challenging to maintain, right? And transactions and all that stuff. So yeah, that's another topic for another day. I'm gonna continue reading about this more. I'm referencing a lot of resources down in the description if you want to learn more about this. Thank you so much for watching. I'm gonna see you on the next one. You guys stay awesome.